All right, so you'll notice that in the previous example, we were solving for a homogeneous equation equal to 0, which means really what we were finding was the null space. Well, for eigenvectors and eigenvalues, we call the null space the eigenspace. So the null space equals almost, actually, I'm going to put an almost in there, the eigenspace. Actually, I take that back. It does equal the eigenspace, but here our null space isn't complete because we would also need to include the trivial vector of 0, 0. So the eigenspace is going to be our 0 vector union with the solutions of a minus lambda I x equals 0. If we take only the linearly independent vectors, then we've got our basis. So here we've got all our multiples. If we look at just 1, 2, then we would have the eigenbasis. So eigenbasis, goodness, sorry. The linearly independent vectors of the eigenspace. Notice that this one and this one are not the same eigenspace. We have individual eigenspaces for individual values, eigenvalues. So for in example 1, for lambda equals 3, the eigenspace is our solution. 1, 2, t element of reals. And this time I can leave t as an element of reals because I want to include the 0, 0. I don't have to say excluding 0. And the eigenbasis would be the 0 vector and our 1, 2 vector. And actually, we don't even need to include this because the 1, 2 would end up turning into 0 as one of our linear factors. So I'm going to go ahead and take that back out. All right, so there you go, eigenspace and eigenbasis.